Next, we have Dr. Jonathan Richard Schwarz, who is head of AI at Thomson Reuters, giving us a talk about data efficiency, how to make the most of our data. Jonathan has had a very rich career as a researcher in AI, we're doing some seminal work at Google DeepMind, a stint at Harvard as well, and now moving on to Reuters, where I learned that they're building out a foundational model department, which Jonathan is leading. And I kind of think of this, through his career, he's tackled many of the open problems of AI, so meta-learning, continual learning, and many others. But I think there's something quite funny here where if I think of a journalist, I kind of think of this being an industry where they really strive to unlock the most potential from their data. And I'll be very interested to hear from Jonathan whether he's gained any experience or learnings of the human biases that allow journalists to do that while working at Reuters compared to DeepMind, Harvard, and some of these other institutions. So this will be the first of two talks directly addressing LLMs. We're going to hear from Jonathan now about using rich data sources, compression, and then afterwards we're going to hear a talk which might focus on some of the socio-technical limitations, which I'll introduce after. So, Jonathan, thank you very much.
Thank you so much.
Take it away.
Can everybody hear me? Okay, good. Well, thank you all for coming, and thank you. That's not on? Okay. Test, test. Working now? Maybe if I borrow yours?
Would you take that one?
Working now? Great. Test, is this working? Okay, sounds like it. Cool. So sorry for that, and thank you all for coming to the session today. I'm Jonathan. I'm the head of AI research at Thomson Reuters. We're just setting up a new foundational machine learning group, so anyone interested in the questions I'm going to talk about, please reach out afterwards. I've got my social media here. As you can see, I'm not very good at concise talk titles, and ChatGPT was not helpful in this case. But what this talk is really about is, I think, a sort of framework, both for researchers to think about algorithms and how we can train foundation models in more efficient ways, but also a sort of kind of frame of mind that I think is really helpful in terms of actually taking this big potential that everybody agrees we have with AI and applying it into kind of complex industries where we are hoping for real kind of automation and productivity growth. And so at the end of the talk, I will speak a little bit about my personal experience in entrepreneurship and industry and how the sort of algorithmic thinking translates into leading teams that come from various different experiences. So what's the argument for this talk? So first, I would argue that around 2020, 2021, we've had a shift in deep learning research from a place where previously people would primarily think about architectures and algorithms and would think very carefully about what's the right network architecture for my problem, to a point where we're now at the position, if you read some of the latest kind of tech reports from these big tech companies, usually we have a small subset of algorithms that are really deeply established and are effectively not touched. So with similar, almost exactly the same optimization algorithms, almost exactly the same kind of architectures, and instead a lot of the real progress that is driven, that is really pushing on these benchmarks is a big new kind of emphasis on data, on thinking about what type of data actually enables reasoning, how can we generate data such that we can reduce the human cost, how can we think about data for safety and robustness. Despite this, I would argue that there's now increasing evidence that some of these inherent data properties make large-scale training protocols unnecessarily inefficient. And as part of this kind of new emerging field, we're now seeing evidence across a whole range of domains, and we saw about RL earlier, that we can possibly achieve better models using less data and shorter training runs. And I'll give some examples of this throughout the talk. And then finally, I think these really big questions that are critical to many here, and I think we'll hear about them in the next talk, fairness, bias, harmfulness, out-of-distribution failures, understanding where these models fail, is a lot of this is inherently rooted in the data distributions. So this is not to say that just working in data solves these problems, but often if you work in medicine, if you think about how do I ensure that I have kind of consistent results for ethnic minorities, if you're trying to understand exactly what sort of task models aren't good at, or similar kind of questions, data distributions are the way to look at it. And if we need any sort of existence proof, we just have to think about how the alignment step works in the final stage of LLM training. Quite literally, the prompt distribution that we give annotators effectively specify what sort of topics in life we want these models to have some sort of moral values about. And so I think these arguments lead us to this kind of new, I think, emerging idea of data-centric machine learning. It comes in various different names and has connections to a whole range of different things, but it's really kind of an emerging trend that has been appearing over the last 2 years. Personally, I've worked on these ideas in biomedicine, in computer graphics, in data compression, in language model training, and image classification, and we repeatedly see similar ideas really kind of helping with efficient training. So what's the argument? This is the second claim here is quite bold. So I'm suggesting that we can somehow get better results with less data and achieve shorter training runs. This goes a little bit against the common kind of argument that all we have to do is scale the kind of data distributions and the model. Here's a little sketch of how data set size relates to information. In the ideal setting, we have the diagonal, where every single data point has the same marginal information value. And so as we collect more data, we kind of cover more and more information. In reality, usually you have something of a log scale, where eventually the kind of marginal value of additional data decreases as you kind of increase your data sets. Another way of saying the same things is usually we have this kind of distribution, where if we flip the axes, the vast majority of data actually captures a relatively small amount of the entire spectrum of information we want to see. And this is probably true in language, it's probably true in reinforcement learning, where perhaps we get lots of demonstrations that are similar, but only later on we might get demonstrations where really interesting exploration is happening. And so the kind of key argument here is that the marginal information content asymptotically diminishes as data volume increases. Now, here's a little sketch that I'll come back to. So most of you will probably know the way we train these models is we initialize at random and then take millions or billions of training steps. At each point, we have a small subset of the total data set. And so this is indicated here by these kind of blue dots. Now, what happens when you combine these two ideas together? We have random sampling of a distribution that is skewed in this fashion. What we'll get most of the time are samples within our training batches that effectively cover information that we might have seen many times before. And so I think part of the reason we are training for longer times is that it takes, just statistically speaking, a long time until we get enough exposure to this long tail of the distribution, where perhaps there's the interesting reasoning problems and something we want to improve on. In addition to this, I think there's increasing kind of evidence that there are certain limits or at least suboptimal progress in terms of pre-training for transfer. And so in this paper that I quite like from 2021, we're plotting the pre-training performance against downstream performance. Each of these dots here is a different experiment, so this is quite a large-scale study. And what we see for multiple downstream tasks is that we get this kind of saturating effect, right? So again, as you move from left to right on the x-axis, you do get better pre-training performance, but this doesn't necessarily give you better transfer. And we can see similar things for multiple tasks. Now, it's not the case that continued pre-training doesn't help, and in fact, that would probably go against the consensus. It's just saying that as we continue to pre-train, we have effectively a diminishing return in terms of downstream transfer. And my argument here is that this has a huge potential for large savings in the sense that we might be able to stop foundation model training earlier or to actually break saturation. Okay, so going back to this very simple diagram I have, how can we think about data-efficient learning and data-centric machine learning? Well, one simple idea is instead of sort of picking data points at random, we really want a sort of prioritization of data points at each point in training, where we're trying to prioritize data points according to their expected model improvement. So here's an open problem. I think the session was about open problems. Really what we would like is some sort of function where RK, this is a ranking function that we compute over the entire data set, such that at each point in training we pick an optimal subset of training. This is the sort of novel data, this concept of new ideas that we want to see that basically allows us to continue learning in the optimal way and stop repeating things we already know. Or in fact, actually filter noisy data as well. So there's a lot of methods that specify this ranking function RK. A lot of them are heuristics, some of them are incomplete, some of them are expensive. So what we really want is a sort of compute-efficient setting. We want model, modality, and algorithm-agnostic settings. We want them to be robust to label and feature noise. We want them applicable online, so in the sense that you could either prune the dataset in advance, but optimally at different stages of training you prioritize differently. Interpretable, because one of the benefits of having this is it allows you to understand which additional data should I be collecting, right? So you can kind of avoid all of this additional cost of collecting data that doesn't really drive progress. And then finally, ideally, you want some theoretical guarantees. So having spoken of the motivation, I want to share some recent impressive results. So this is a result from Datacom 2023, where we had CLIP, this is a vision language model, trained on about 12.8 billion examples, and this is the zero-shot performance that we get. And these researchers were able to reduce the data set size by 90% and get an uplift in performance, okay? Here's another result. So this is now for language model training on 7 billion models. I think this is a kind of mathematics data set. The dashed line here is the performance we get if we train on the entire data set, okay? And so if we move from left to right, we kind of prune more and more of the data. Actually, from left to right, we increase the data set size, but notice that I'm ending the axis here at about 40%. And so in this case, again, we get a 90% reduction of the data set size that we have and still improve the result. I think a secondary effect of this plot is there's a lot of methods here. And so that's why it's an interesting open area to work in, because we're far away from having like a default algorithm you can just use. Here's a paper that will appear in Europe's 2024 that I was involved in. This is for language model pre-training or continued pre-training. Again, we were able to show stronger results, faster learning, and in this particular case to achieve this kind of cross entropy with about 25% less data in this case. Similar things hold true for instruction tuning. So anyone who's thinking about perhaps any kind of applied sort of language modeling setting, you can now kind of understand, characterize what is the task you really care about, and then pick from a wide range of different language modeling data sets, and you can kind of align the gradients of training data, validation data, and you can get to a point where using 5% of the initial data gives you a stronger or the same results. And because data is effectively a compute multiplier, it means that you can train much faster. In addition to this, having understood that you only need 5% of your data, any additional data you can collect, you can be now a lot more specific and strategic about. This is for the popular image classification data set. Once again, roughly half the training time. In this case, quite literally about half and half the data. This is a result that we achieved this year as well. So we had a 50% speed up, but what's even nicer, as we continue training, we actually outperform the baseline here by 15 to 20%. And these are not small scale problems. So in some of these problems, we have, again, billion models in the size of billions and data sets with hundreds of millions of examples, if not billions. So you might wonder, what's the catch? Why isn't that something that everyone's using already? There's a couple of other things, but I think one of the things that has been repeatedly noticed is that for sort of suboptimal choices of RK, we might actually end up with computation of this function being more expensive than the savings, right? And so, what's the point of you doing that, right? This is the same paper I just showed that gave us this 50% boost. What I'm showing here, these kind of green bars are basically showing you the compute costs of training. So in the original setting, we had the training of our learner kind of took this amount of time. We had a new ranking function that we call the learnability criterion. And again, without any changes to hyperparameters, the algorithm, the architecture, you get about a 25% to about 1/3 speed up. But one of the things that people in the literature do, they're not necessarily fully honest about the additional cost. And so I'm adding up additional kind of like bars in different colors that show you the cost of actually computing the ranking function, okay? So you end up, in this case, spending more time. So how do we get out of this? The idea of this work is to ask, do bad students actually make great teachers? In other words, can we use smaller models of the same architecture to learn about a data distribution and then reapply what we've learned to bigger models? And this kind of comes to this idea of foundational curricula. Perhaps we can actually learn about how we should be scheduling data with small models and then transfer this kind of notion to bigger model training. And indeed, what we've shown as we kind of look at smaller models and looking at those as a kind of proxy to the large model training, we start actually realizing real gains, this time tallying up correctly and adding everything. And if you think that some of these big model trainings can take hundreds of millions of dollars for a single training run, just saving 25% is a huge saving and allows you to experiment more, create better models. So here's an example. This was an image classification using 300 million examples. Again, this is about a 46% speed up in this case. I showed this one already. We had both a speed up and finally the kind of models would continue to improve. Another place we find kind of data-centric techniques work is in catastrophic forgetting. So for those who aren't familiar, one common way of working is to take a foundation model, which is characterized by a sort of skill set across a large range of tasks, so coding, maths, reasoning, multilingual. And if you're kind of a startup or you work in industry, often the idea is that we collect some sort of domain-specific data and then create a version of this model which has kind of broadly the same kind of skill set, but is enhanced, say, in medicine or at Thomson Reuters in legal settings. In practice, what you find is that, yes, you might get a boost in legal settings, but at the same time, you get this catastrophic forgetting problem. Because you're not like relearning these other skills, you get a contraction of the skills. And all of a sudden, you don't really know exactly what things you've forgotten, and this is sort of difficult to characterize. This is a slightly older paper of ours where we've been trying to kind of come up with ways in which we can use the simple idea of rehearsal or pseudo-rehearsal. So obviously, let's replay some data from the past so we get less forgetting. What we did here, we specified a kind of statistically motivated technique to find an optimal subset of data that we can replay. For the experts in the room, this was sort of based on sparse variational Gaussian processes where people have spent a long time thinking about how can I reduce my data set size in a principled fashion. And if we now looked at some results, this is over a range of training 10 tasks in a sequence. If you do that in a way in which you don't get catastrophic forgetting, you get about sort of 86 to 88% performance. With catastrophic forgetting, you drop down to 26%. Now, there's a couple of techniques we compared against. All of these tend to be architecture or method focused. So we get up to 70%. With these data-centric techniques that are interpretable, have other advantages, we get up to 81%. In addition to this, we've seen kind of a bigger emphasis on focus on synthetic and hybrid data. This is another kind of view of data-centric ML. So NVIDIA writes that 98% of their recent model, released in August, so just 2 months ago now, 98% of the data used for their model, alignment process is synthetically generated. Those who know, alignment usually requires a lot of interaction with your annotators. So these are real savings. Meta write as well, we use synthetic data generation to produce the vast majority of our supervised fine-tuning examples, iterating multiple times to produce higher and higher quality synthetic data across all capabilities. Right? So all of these developers thinking very carefully about how they can measure data quality anticipated. Google DeepMind writes, we find that data quality is an important factor for highly performing models and believe that many interesting questions remain around finding the optimal data set distribution for pre-training. Right? So if you're a young researcher, or student, or just sort of looking for the next problem to work on, this data-centric machine learning question is a really, really pressing problem. And I think it's still very early days and the kind of best techniques are yet to be defined. Okay. Because this is a broad audience, we've heard about from people in public institutions, from government, from startups, I wanted to take a small detour and speak a little bit about how this data-centric perspective helps us kind of build institutions that are collaborative between experts from different domains. So this is a little bit of my personal story. This is the story of SafeSign Technologies, a kind of startup we founded in October 2023, so roughly a year ago now, and that we took from a founding position to an acquisition within the space of about 10 months. And I think a big reason was, yes, we had good models that were outperforming these other providers, but in addition to this, we really kind of managed to demonstrate how do you combine experts from different domains. In this case, AI in the legal world. So this is a setting where we've got a big, complex field where people study for a long time. It's expensive. There's questions about access to justice. So this is really kind of the sort of problem we wanted to use AI for. Now, the way that I'm going to present this is in a sort of pyramid, and how data-centric machine learning comes into action is we really think of the kind of 2 bottom layers of this pyramid as the point where legal experts can come in. And they come in primarily through the lens of data, because that's what they understand best, and that's what the machine learning researchers typically have less experience of. Okay? So what you do is you build taxonomies of data coverage across large, complex fields. We quite literally did that with tenured professors at the University of Cambridge that are part of the startup. You do targeted annotation towards gaps, and just sort of using a third-party service where you get a kind of a random number of people across the world that annotate data for you is not going to cut it in terms of data quality. And that allows you also to kind of quality check these things. You get these people to do continued adversarial testing. So you get kind of repeated experimentation with these models. You really test them in with experts in their specific domains, because these people know what is the most kind of work-heavy workflow in terms of their industry. And that allows you to kind of get really fine-grained model critique and understand more where you have to collect data. You then augment the setting with hybrid data approaches, so the sort of synthetic data generation we heard before. But instead of just doing this blindly, you really want to make sure that you understand, the experts tell you which part you're missing out, so that you can generate data in a targeted fashion. And really only at this point, so this is primarily still sort of expert information, and really only up at this point you start introducing kind of the machine learning intelligence. So this is where we introduce this data-centric machine learning techniques around what I spoke about, continual learning. This is the catastrophic forgetting problem, about automated curriculum learning. And then in addition to this, you probably want to think a little bit about post-training techniques. Now, you might think this is just the sort of story of one startup, and I'm patting myself on the back, but I think this is really a helpful way of thinking about how you can kind of bring machine learning to other domains where you want to realize these gains in a real way. And this kind of model basically started with a group of about 10, 15 people, roughly half machine learning, half in the legal world, is now being scaled up to about thousands of subject matter experts, a big machine learning team, which brings me to kind of the last slide. We're building a new foundational research team. We have a big investment in compute. We have academic partnerships that are really exciting. So if anyone is interested, please reach out to me. Thank you.
Hello.
Hi.
Hello, thanks very much for your talk. I was wondering what's your comments on manifold hypothesis, or maybe it's manifold the right things look at how to characterize the low dimensionality or sparsity of the data?
I not necessarily have deep thoughts on this particular hypothesis. I think in terms of the characterization of this, the best thing we know in terms of kind of theoretical guarantees usually are centered around techniques that are trying to somehow look at kind of getting a subset of your data and the gradients to be representative of the gradients you get with the full data. And that's kind of when you start kind of building a kind of theoretical guarantees of the kind of model improvement you can get. I'm not sure that really answers the question, but that's probably how I would think about sort of understanding subsets of data in a principled fashion.
So if no further questions, let's thank Jonathan again. Thank you very much.